Hey, Physics 111. All right, I'm going to do some videos on Chapter 14, which is about fluids. So a fluid is any substance that can flow. So although we might normally think of a fluid as just being a liquid, actually a gas is also a fluid, and so would a plasma, which is basically a gas. It has lots and lots of charged particles in it. So because this is still material and it still has a mass, it's got to follow all the rules that we've talked about so far. Like, if you shoot a fluid up into the air, it's going to have projectile motion, which is sort of what a fountain is. It's going to, if you can exert a force on it, it's going to be accelerated. All those things are still going to be true, but it's really hard to talk about mass when you talk about a fluid because, it's not discrete. In other words, regular mass, we think about it and here's the mass, and then, there's an end to it. There's a volume, set volume it takes up. But, and there's a center of mass and everything. But with a fluid, it's, when do you stop counting the mass? So instead of mass and F net forces, we're going to have, instead of these, we're going to talk about density and pressure. So density, which is little rho, so this is Greek letter rho, it's the lowercase version of it, and it's the mass of your substance divided by its volume. And although with a fluid, you're not going to be able to say where's the end of the mass or where's the end of the volume. With a fluid, you have usually a set density, or at least a constant density, a uniform density inside at least your volume you're dealing with. And so we can talk about density even though we can't talk about mass. So writing this out, we have mass on the top, and then capital V is our volume, is what we're going to use for volume. Those almost look like they're squared or something. Unit-wise, this turns into kilograms over meter cubed. It could also, sometimes you see things in maybe grams per centimeters cubed. It really can be any mass unit divided by any volume unit, which is going to be a length cubed. All right, and then there's pressure, which is in every other textbook, physics textbook, is going to be capital P. Your textbook, one of the few things I don't like about it is that it uses a little p, but I'm not going to do that. So capital P, this is pressure. This is the same capital P that's in the ideal gas law, which is probably one of the big things it's in. And that's the same capital V, by the way, for volume. And pressure is a force divided by an area, but it's really talking about the forces being applied onto a certain area. And so you're spreading the force out onto an area, and the smaller the area that the force is acting on, the larger the pressure, the larger the area, the smaller the pressure. And so there's this relationship. Instead of force, we're going to talk about pressure. Unit-wise, so if you have force over area, that means we have newtons for force, and meters squared for area is our SI unit, which is actually its own unit called a Pascal. There are lots of other units for for pressure, and we'll talk about some of those probably, or some examples as we move along. So a little bit more about density. Densities, most objects, most fluids have, most liquids have sort of known densities or standard densities. They are temperature and pressure dependent, but generally they're fairly well known, and so they can stay constant. A gas is going to have sort of variable pressure, but even inside a volume, so if you set a thing of gas inside a box, it's going to have immediately a uniform density. So the density will be the same throughout this volume. It just fills it up, and it's not denser in one location than another. It's the same density. So you should be able to have sort of a constant or uniform density for your fluid, which is why we like it. Pressure So let's see if I can do this and reload it. It wants me to have a subscription, but I'm not going to buy a subscription. So here, this is just a sort of a demonstration. So this is a syringe with a plunger that can push on this material, and it can cause an increase in pressure. And this is actually a gauge that's reading pressure. It's reading it in atmospheric pressure. So we can actually see the molecules. So the pressure actually comes from the molecules bouncing and hitting off of the plunger here. And this is actually an elastic collision. And you can use the fact that these are elastic collisions to actually derive the ideal gas law. And I may do that later when we talk about thermal physics. But what I can do here is I can actually push, and as I push on the plunger, I'm actually getting a higher pressure on the gauge. I can actually pull the plunger out, and I get a lower pressure. And this is, again, I'm exerting a force on the plunger. It's acting on the area, which is the area of that space right there, and we get an increase in pressure. We'll reload it one more time. So I was doing a force on the plunger, but the plunger can actually do a force on, the gas can also actually do a force on the plunger. So if I let it go, it pushes it right back out again. That's a force being exerted by the fluid on this. So in either way, they can both, fluids can get, you can exert a force on a fluid by pushing on an area, or you can also have the fluid exert a force on the area. Either way, these are pressures. In 1 atmosphere, so the atmospheric pressure, this is basically the average pressure from the Earth's atmosphere at sea level. And it's 1.013 times 10 to the 5 pascals. All right. Now, I think we know that if you went up in the atmosphere, the atmospheric pressure would get lower. Certainly, I think you probably experienced that if you go deeper in the ocean or even in a deep swimming pool, the pressure gets higher. And so there is a dependence on pressure with the depth inside a fluid. In the case of the atmosphere, it's coming from the actual gas molecules that make up the atmosphere of the Earth, and they push down and they cause a certain amount of pressure. And we can actually derive how pressure changes with depth in the fluid. So if you have, say, some fluid, say this is in the ocean, or even a swimming pool or something like that, and we're going down into the water or our fluid. As we reach some location, we'll say that the pressure here is P1, and that's at Y1. So we have P1 and Y1. And as we go deeper, we might have a different pressure at this different location, this different vertical depth. And the difference between Y1 and Y2 is H. Now, there's a force being exerted on the top of this fake cylinder. So I'm just putting some hypothetical object there just so I can do some geometry but the actual size of this cylinder turns out to not matter at all. So there's going to be a force that's being exerted on the top of this cylinder down, which would be force 1. And force 1, according to the rules about pressure, is the pressure 1 times the area of the top of this cylinder. There's also a force being exerted at the bottom of the cylinder by pressure 2, which is pressure 2 times A. Now there's also forces being exerted on the side here, but those are all canceling out with each other. Whatever force I have on the side here equals the same force on the other side because the pressures are the same at each depth. If the pressure is P1 on this side, it's also P1 on that side. It's the same at all those depths. And then there's also the fact that inside this cylinder, there's a certain amount of mass. And so there's a gravitational force pulling down on the additional mass that exists between Y1 and Y2. right? There's more mass that's pushing down. So, and then, chunks of the ocean don't rise or fall. Water inside your pool isn't moving up and down. It's stable at that location, and so we could say the acceleration is 0. So math-wise, we end up with F2 minus F1 and mg. We have 2 forces down, 1 force up, has to equal 0. Plugging in what the forces are, we end up with P2a minus P1a minus mg equals 0. The mass, I can rewrite the mass. I can say the mass of the fluid in there is the density of the fluid times the volume of this cylinder. The volume of the cylinder is A times H. It's the area at the bottom of the top of the cylinder times the height, or, you probably are more used to this for the volume of a cylinder. But all I really need is the A, where A is that pi r squared, where r would be the radius of the cylinder. But I can plug in this for mass over here. And all of a sudden I have an A in every term. The area here. In fact, that means that it doesn't really matter. I didn't have to have some fake object in there at all to do this. The force pushing down, or the pressure causing forces pushing up, has to balance the pressure and this rho GH, which is almost like the gravitational potential energy per volume. Yeah. So we end up with this. Rewriting that, it basically says the pressure at the bottom is equal to the pressure at the top plus this rho GH term. So it's balancing off. There has to be more pressure at the bottom to balance the fact that not only do you have pressure at the top, but you also have this gravitational force trying to pull down. And pressure gets larger at lower depths because of this. And I did do number 13 in the Zoom class on Thursday, and that is available on YouTube and on our web, I think our class, just YouTube, and then the notes too, so you can go look on there if you need any help on number 13. All right, to measure the pressure, so we have to be able to measure pressure, and there's actually 2 sort of ways we measure pressure. There's 2 ways we quantify pressure. One is absolute pressure, and this is what we need most of the time, especially to do any kind of equations and stuff with. The ideal gas law is looking for that real pressure. Most fields like chemistry or weather, things like that, meteorology, are all going to measure pressure and absolute pressure. And to do this, you use a barometer. And essentially, a barometer, you're going to measure the height of a fluid in a tube where one end of the tube is exposed to a vacuum, which means it has 0 pressure, and the other end is exposed to your sample, which has the P you want to know, right? It's got the pressure you want to know. And so it really looks like this is a very crude-looking, old-fashioned sort of barometer, but you have a vacuum, you have a tube here. This is some fluid. Typically, it used to be mercury. Now it's more likely to be some sort of alcohol or water if you actually use this kind of barometer, because mercury is highly toxic. But you have pressure at the top you have 0 pressure at the top from the vacuum, and then at the bottom you have this open and exposed so that the pressure here is exposed to your sample, and so this would be your sample. Looking at our equation that we just had, where we said pressure at the bottom, which is our P, is equal to pressure at the top, which is 0, is equal to rho GH, where rho is the density of whatever fluid you're using. If P at the top is 0, then we just have that the absolute pressure is going to be the height that you measure times G times the density of the fluid that's inside your barometer. And it's really very simple. And this works, again, because you have vacuum at the other end. You have a vacuum at the other end, which means that the pressure at the top is 0. Now, gauge pressure is used in some other fields or some other applications. So gauge pressure is written as P little g, and it's actually the difference between the absolute pressure and the atmospheric pressure. So it's essentially how much more pressure is there than the atmospheric pressure. That's what the gauge pressure will tell you. It doesn't tell you the absolute pressure, it just tells you how much more is there than the atmosphere. So that's why with tires, we don't care what the absolute pressure is in a tire. We care how much more pressure is there compared to the atmospheric pressure. You need to have more pressure in a tire so that it can hold up the car. You can't have atmospheric pressure in the gas inside your tire, or it would be a flat tire. Now, gauge pressure is also going to have the equation rho GH, because here we're using an open tube manometer. So we still have a tube, we're still exposing our pressure, our tube at one end to our sample. But at the other end, instead of having pressure equal to 0 at the other end, now we have atmospheric pressure. So we have an open tube manometer where one end is open to the atmosphere instead of vacuum, and the other's to the sample. So when we measure the H here, that's going to be the pressure of our sample minus the pressure of our atmosphere. Or the pressure is going to be the atmospheric pressure plus rho GH, but we don't really get that. So the gauge pressure is this rho GH, where somebody goes out and they measure the H off of their open tube manometer, and that they just multiply that again times G and the density of the fluid, but that's telling them the gauge pressure, not the actual absolute pressure. Now, because pressure has existed for a long time, this is one of the first things scientists started to measure when they got into labs and such. And that always ends up giving us a lot of different possible units because of various conventions that existed throughout the world when people started measuring these things. But it also meant that because the scientists who were doing this, what they were really measuring every time was height. And so that's what they would write down in their little, books. They'd say, okay, here's the date, and they would write down the height. And they probably didn't usually turn it into necessarily a pressure, assuming they even knew the physics behind this. They just said, this is how high the tube is, this is how high the tube is, this is how high the tube is. That has meant that we've ended up with some very strange units for pressure. Examples, blood pressure, you end up with millimeters of mercury, or sometimes centimeters of mercury, or maybe even now we might have inches of H2O. Those look like distances, they look like lengths, and lengths are not the correct unit for pressure. Pressure should have newtons per area. It should have force per area, and length is not force per area, but it's just a convention, and these units prevail and are the dominant units for many, many, many fields. So it's just one of those things you kind of have to know what it is. So this question, number 25, is actually taking a measurement of H and determining what the absolute pressure is, because this is a barometer. So here, in number 25, it says that someone goes out and they measure that the column, the length of this is H is 740.35 millimeters. So one way to write this pressure, and this is mercury, is you could write this at 740.35 millimeters of mercury. That is a technically correct unit And it does mean a pressure, even though it looks really weird. But we want to get the pressure in pascals and then in torr, which is another used unit for barometer measurements. So we're going to remember that this is absolute pressure, so it's rho, and in this case our fluid is the density times G times H. Now they're being very specific with us, and they're telling us that at this density, at this pressure and density, or at this temperature, the density of mercury is this value, and that G at this location is a little different than 9.80. And so we're going to plug in those numbers. For the density, we get 1.3608 times 10 to the 4 kilograms meter cubed. For G, we'll put 9.7835 meters per second squared. And then H, we have to convert this to meters. So 0.74035 meters. And let me do that math. All right, so multiplying that, I get 9.8566 times 10 to the 4 pascals. I got 5 significant figures in my givens, and so I need to have at least 5 significant figures in my answer. That's part A. For part B, they want us to convert this to torr. So if this is my thing in Pascal, 1 torr, and I think I had this, oh, it's gone now. 1 torr, and you can Google things like this, is 1.33322 pascals. So I'm going to say, okay, 1 torr is 133.322 pascals, and I end up with 739.31 torr. Okay, so I'm going to end this video here, and then I'll move into some other stuff in chapter 14, the next one.